Hello, welcome to this short presentation on extended time regular expressions. Currently, we are developing a number of theories, tools, and this is the team involved up to this point. We start by looking into regular expressions. This is uh, a classical problem that appears in industry every day, and the main use of regular expressions. Here we are given a corpus, text, and as you see, there are some emails. Now we would like to collect all the emails in this text. How is this being done so far? Well, the current approach is to describe a regular expression that describes the set of all possible emails. This is a simplified regular expression. Here you can see that describes the set of all emails. Now, this uh, expression is going to be transformed into a finite automata, and then the finite automata is going to, the text is going to be simulated over this finite automata, and it's going to use to do the matching. For example, one would naively traverse all the text, and then, for example, here, we will check if this subword or factor belongs to this set of regular elements induced by this regular expression. If this is correct, then we have found a match. This is known as pattern matching. So we are given a pattern and then some corpus, and then we need to find the factors of the corpus that fit in the pattern. According to Gemini, there are billions, if not trillions, of these kind of operations every day. Now, we have seen how regular expressions are used to do pattern matching in words, in text. Now we have a particular case of words. These are words with time. For example, time series data. Here we have time series data for the heartbeat of a patient. In blue, we have the heartbeats, and in orange, we have the medical annotations. The annotations indicate if there was a normal heartbeat, or in this case, we see here this orange going up indicates that there was a heartbeat that was too early. As we can see here, these two heartbeats are very close to each other, and this is a sign of arrhythmia. Of course, now what we would like to do is to find these patterns in these timed words. Another case is, for example, we have the Aalborg University building built that provides different channels. Here we have time series data for the heater and the ventilation. And here we also would like to find some patterns. Then the challenge is how can we express complex timed patterns, for example, the arrhythmia case, or in this scenario, we would like to find this part here where the system is heating and cooling at the same time, very inefficient. In order to define this language, we will need to define what are events, and then some instance of time pattern matching for time series data. We start by defining our events, formalizing what are time words. For this, we're going to use a structure that is the time event monoid introduced in the work from Azarin, Caspi, and Mahler in '97, where they present time regular expressions. So we're going to extend the classic monoid from them by adding vectors over the reals, right? So now our sigma are going to be vectors over the reals, which will allow us to encode time series data. And we have positive reals, which are used for the time elapses. So here we have our data, but now if we consider how data looks in the real life, it looks as follows, right? It's not really continuous. We have finite discrete points, and this kind of data can be naturally be described using this monoid as follows. We have the first element, the first duration of 0 concatenated with a vector with the values 100 and 0. Here we see that we have 100 in the heating and 0 in the ventilation. Then the next point is a duration of 2 time units have elapsed, and the values are again 100 and 0. And then we can keep going. We have the durations between events and the events encoded as a time word. With time words being formalized, we are able to define or extend time regular expressions. We are our goal is to apply this to big data, and therefore we are trying to do already optimizations. For example, we have a grammar where we have 2 levels, and we are allowing intersection only at the first level. We don't have nested intersections. However, note that having nested intersections would be not an issue. It would be just computing the product, which is very expensive, right? We have to do uh, the product composition syntactically before running the system, and this will go exponentially big on the number of components. So we have no limitations in expressiveness, but if we want to be fast, it's best to have it at the higher level because we are going to have networks of automata. The semantics for a regular expression give a set of elements in the time event monoid. For example, now let's consider some atoms. Our atoms are, for example, this expression see here, this constant, we have sigma, which is all the alphabet. We have functions and the time constraint operator, plus the traditional regular expression operators, the star operator. The semantics, for example, for this expression, constant I delta, give a set of elements of the monoid. Let's look as an example. Here we have the constant is 80, the dimension is heat, and the delta is 20. So what this means is graphically here. This gives us all the points where we have the dimension heat, whereas the other dimension, the ventilation, so we have 2 components, heat and ventilation. The ventilation is unrestricted, and heat is restricted to the values of 80 plus minus 20, so 60 to 100. And visually, we see here 80 plus minus 20. Now, if we have a signal like this, and we run the pattern matching, of course, all elements that intersect with this blue area should be detected. I can show you briefly our tool. In our tool, in our tool, as you can see here, we can write now these expressions. So let's if we see this plot from the arrhythmia, we see values. Let's assume we want to match the heartbeats, right? These peaks. Then an expression could be like, we see that this is around 1.1, right? So we can do that. We want to match the value 1.1 in the MLI, right? This is the channel 1. So we want to match in the dimension 1, and we can describe a delta. So let's put a small delta, 0.01. Then we can see if there are matches. It found 4 matches, like these, and these, and these, right? So these values match with this constant. Let's assume we want to match more. So maybe we can increase our delta. Let's increase it to 0.1. If we run, now we have all the peaks except one. Okay, let's just increase a little bit the delta. So let's put here the value 0.2. Let's run again. We have now all the peaks. But let's observe in more detail. Here, for example, this match. You can see here that we had 2 matches, like this and this. Okay, so there is some redundancy, but we have successfully matched all the peaks. Let's go back to the presentation. Now, another expression that we allow is the use of these functions. These are more complex. What a function do is it kind of describes sequences of duration between D1 and D2, where the it component, or the signal, the it signal, is delta close to F. For example, for the detecting the arrhythmia, maybe it is better to use a polynomial to describe the heartbeat. So we are going to use this 5th degree polynomial to describe this this heartbeat. So the delta is the width of this tube, and it describes all the sequences, right? All the words that are inside this tube that have duration between D1 and D2. So basically this sequence here, like it can go like this. This sequence, such that it ends between D1 and D2, would be matched. If we see our tool, it has some examples. We can open this example. This has some polynomial. Here, you see the polynomial has a name, a function is on the first dimension, which is the MLII. There is a delta of 0.33, a duration. This is, I think, nanoseconds. So the duration of the word should be between this inside this interval, and these numbers are the coefficients. Note that since it's a 5th degree polynomial and we have very small numbers, you see coefficients like to the power of minus 36 or minus 44. So we have to use a multi-precision library. Now we can match this polynomial in the data, and it gives us these matches. We see here in red is not matching all. What we can do is either modify the polynomial, find different coefficients, or we can increase the delta, the width of the tube, and it will give us more matches, right? So we resume the presentation. In the paper from time regular expressions from Azarin, Caspian, Mahler, 97, it is shown that time regular expressions and time automata are equivalent in expressiveness. And therefore, in the same way as pattern matching uses finite automata for doing matching in text, we can use time automata to do pattern matching in the timed words. Let's observe how can we encode this time series data and the corresponding time word in a time automata. So extended time automata has discrete variables. In this case, these are real value variables, this BA1 and BAN, one variable per channel. So in this case, heater and ventilation, we will have only two discrete variables to store these values. We have clocks, and we have synchronizations. If we observe this word, the first part is a duration, a delay, and then the event. In the automata, we have a clock that is going to delay from 0 to t0, and then at point in time t0 is going to take this edge, right? So we do the delay, then we update the variables with the values of the events, and then we move to the next delay. And so on, we can do the delays and update the events, and this automaton, this finite extended time automaton encodes this word. So now our challenge is to, if we are given a time word and an extended time regular expression phi, we need to decide if the word belongs to the set induced by this regular expression. We are gonna do this using a translation similar to the one presented in the paper from 97, where we transform extended time regular expressions to extended time automata. So then we will have our word, then we will have a network of automata encoding the expression, and then what we need to do is to check if the product is accepting, if the network is accepting. Now the construction of the automata from the expression is very similar to the original construction for finite automata and also for timed automata. However, we have some differences. We have the synchronizations, and in particular, you see this LU. This is an urgent location. This is a location where time cannot elapse. So we are very careful introducing these urgent locations to know when time can elapse. So we have this translation, we transform to time automata, and then we have some invariants on the structure, on the syntactic structure of the network. We have stuff like initial locations are not accepting locations. We know that a location is not urgent if and only if it is accepting or if it is an input location. So we are very careful with the construction, and then we know the structure of the networks. And this has allow us to prove a number of theorems and lemmas. For example, the following lemma, because of the previous lemma of the shape of the network, we are able to conclude that all the accepting rounds of our system have the following form. First, we start from the initial state. Then there is going to be a number of interleavings in 0 time, meaning that some component is at an urgent location, so no delays. Then there is the first delay, the first duration, the first event synchronization. Then there is another finite number of executions where time is not elapsing, and then we have the second delay of the time word. Then there is the event. Then all the automaton are basically checking in urgently if the data fits in the regular expression, and it keeps doing this. So what we can see is that the only delays that the network is going to have is going to be the delays in the time word. Therefore, basically we are doing discrete time. There is no need for DBMs or zones. It makes our algorithm simpler and faster. In addition, we see that there is an interleaving of sequences where time cannot elapse and then time elapsing. So this makes that we have two-level algorithm, one for dealing with the time and then the other one doing the urgent exploration. And in particular, we have work for doing partial load reduction when in this kind of systems where there are fragments, big fragments of the system where there is no time, then we have this so-called urgent partial reduction, which is implemented here. So if we have a lot of networks, your network is big with a lot of components, and there is urgency, then when there is interleavings, this partial order reduction will kick in. We have correctness. We have that a word belongs in the set induced by a regular expression if and only if the network is accepting. This is the high-level idea of the algorithm for discrete time pattern matching. Basically, we have a time word, and we have a factor or a subword from position I to k. Then we are going to construct the automaton for that subword. Then we have the network for the expression. Then what we need to do is to check if the network is accepting. If the network is accepting, then the subword ik is a match. And okay, so note here we are gonna find only one match, and we just report the first match that we find. Okay, so if we start here at this position and we have this pattern, then we are gonna slide the pattern for every I, right? For every position I, k, we are gonna slide it until it match. When it match, then we store the match and we have a match. Okay. Now we can see some case studies. Here we have the arrhythmia data set. Now it would be tempting to find the heartbeats using just, for example, a constant as we have done, like close to the value 1, right? So this data set for patient 100, it has 650,000 samples and 2,274 medical doctor annotations, which are in orange. So let's try to find this QRS complex or the heartbeats using a constant for values of around 1 with some delta. So if we run the tool and the delta is 0.32 or 0.34, and we run the tool, we are going to see that there is a number of matches. What do we observe here? For example, yeah, there was some heartbeat here also annotated, but there is a number of repetitions here. There is a lot of repetitions. So running this experiment, um, we have 9,500 matches. We know that there are 2,274 which are annotated. So we would like to get close to this number, 2,274. Um, Now, if we take this number and with these matches and we take a conjunction with the annotations, which we can be done in the tool, um, there are only 2,253 matches. So there is a number of repetitions, like what we can see here. So we can do much better by doing a match using this polynomial here, right? So if we do a matching using the polynomial, we see that we have much less repetitions, only 2,400. And we see that we have matched, there are still some repetitions. And yeah, we can say that we have matched all of the medical doctor annotations, but with some repetitions. Then note the time, like matching a constant was 2 seconds for these all the records, more than 500,000. But for using the polynomial, we have 109 seconds. This is in particular because we use this multi-precision library and we have to evaluate a number of times the polynomial, and this is expensive. In our new version, we are now caching the polynomial, the values of the polynomial, and now we are able to do this like in 10 seconds. So we need to update this. The more challenging pattern matching for this is we want to detect arrhythmia. What is this? These are two consecutive heartbeats that are too close. We can define the Euler expression for this. We have the first expression for a heartbeat. Then we concatenate with sigma, the full alphabet. There is no constraint for a duration from 0.04 to 0.6 seconds. So we allow everything. And then after this, it follows another heartbeat. So these are two heartbeats coming close to each other too soon. If we run this expression, we are going to match. We have 94 matches. And if we take a conjunction with the medical annotation, we note that we have 29 and 34. So 29 of 32. So we are still missing some annotations. We are very close to what the medical doctor says, but we are still missing some annotations. And we are also matching things that are not annotated. So here, in this area here, we see that we have matches. And there is no error. This is really matching the expression. So when we look into this data, we will observe that here the patient has changed the activity. So maybe the patient has moved or is running, you could say. So the heartbeats became much closer to each other, and therefore it matches the expression. And maybe the medical doctors look like in this full area, the patient is moving because it's not that the two heartbeats are very close, it's they are regularly close. So it's not that easy to match arrhythmia. It might need a more elaborated expression. Another case study is this one from the building of Aalborg University, which has a number of signals. In this case here, we're interested in matching when the heating and the ventilation are on for an extended period, right? Because if it's heating and cooling at the same time, this is an inefficiency in the building, and we would like to detect this. This can be done using the following expression. We have that the heating is 80% open, plus minus 20, and the ventilation is also 60 plus minus 40 percent open for a duration from 1 to 2 hours. If we run the expression, for example, we get this match here where both heating and ventilation are open, and this is something we need to detect. The data has 233,000 records, which is 23 megabytes, and the time is 2.7 seconds for the matching. The building also has some problem. During the summer, it can be too hot. In some rooms, there is too much sun entering, too much light. And what they would like to do is to have an automatic control that detects the increasing of the sun, the solar watt, and if continuously, and if it happens, then they will decide to close the windows automatically. So we need a good matching, and this can be done using this, for example, this linear function that is increasing in the solar watt for 45 minutes. Then we can run this linear function, and it's going to match this here in red, where the controller can decide to close the window or the blinds. Okay, again, we are very fast matching this, few seconds. Another case study here is the task is to control these gates. Here, they need to satisfy a number of safety objectives. So the goal of these gates in the Vide Sande Harbor is that they have to control the flow of the water between the North Sea and the Ringkøbing Fjord. Okay, so we have collected 14 years of data. This number of samples, like 3/4 of a million of samples in 19 dimensions. And we have encoded several of the safety properties in regular expressions. Let's look up to this, the complement of a property, right? So if we find this is the negation of something good. So if we find a match, this is bad. So the gates should be open only if the difference between the sea and the fjord water is less than 100 centimeters. So we're talking about a difference. This is not in the data. So by doing some pre-processing, we have added a channel diff that has the difference between the two levels. This is in green, right? So green here is the difference between the water in the sea and the water in the fjord. Now we need to match for when the difference is bigger than 100 centimeters. And this is what we have here. We see here that the difference is bigger than minus 100, so bigger than 100. And the gate was not closed. It's open. And we have a match here. This is a violation to the safety property. Now, encoding these properties in regular expressions is, as working with regular expressions, we need some ingenuity to encode properly or to create the expressions. So in this case, for example, we use to say that the gate, the port is open, we are saying that this in the values 51 plus minus 50, right? So this is 51 plus minus 50 give us values from 1 and above. This is a way to say that the gate is open. Okay, so there is some energy needed to design the proper regular expression. We run this different regular expressions on the 14 years of data, we found a number of violations in very few seconds, using almost no memory, 5 megabytes. Another ongoing case study, well, there is a NeoGrid company from Aalborg. They have a pamphlet where they advertise their products. In particular, reading this little text, we detect two properties. So the first property says that the system ensures that the temperature should not come over 60 degrees continuously in Danish. So it's a little bit ambiguous, natural language, but we can encode this. Let's say it should not enter. So a violation would be that the temperature goes in 90 plus minus 25. So this area here in blue for 5 to 6 minutes. So for example, a violation could be we are here and then it enters just for a short time. This is fine, but if it stays long enough, then it would be a violation to our system. Okay. In this way, we can encode this property. And this is kind of easy. Let's look into the second property, a little bit more involved. There are these dangerous Legionella bacteria, right? So the system has a program against these bacteria that ensures that the water is at least 60 degrees for 30 to 120 minutes once every 2 weeks. Now with my colleague Marius, we spent some time thinking on how to encode this, and we came out with this regular expression, which is the complement, right? So something bad is an execution that in 2 weeks is never staying in this red area, is not hot for 30 degrees, right? So what would be something bad? So let's assume we have 2 days. So if we have something that enters but less than 30 minutes, and again enters less than 30 minutes, and again enters less than 30 minutes, this execution will match this expression where it was not long enough in the hot water in 2 weeks, and this would be a violation to the system. Okay, and we have a tool that we have used for our experiments. It's implemented in C++. It can be used for live monitoring or for post-analysis of big data. We have the underlying formalisms with correctness results, with mathematical proofs. Up to our knowledge, there is no commercial alternatives, and we envision a number of extensions and applications. So we have seen mostly the theory and the engine, right? We have also seen briefly use the Python GUI, but we are also building a front end in Flutter where we can have multiple users. It's connected with databases. Also, we can do streaming from systems like Schneider Electric for monitoring. So we are still developing further the tool, but we are also working on the theory. For example, there has been work on doing determinization of the time automata for doing faster matching. We are also working on parametric expressions. Yes, and with this I finish, and I thank you for your attention. Thank you.